Hi, welcome to this session on Haskell informal methods at Cardano Summit 2021. My name's Phil Wadler. I am Senior Research Fellow for IOHK or IOG, if you prefer, and I will let our other panel members introduce themselves. And Manuel is going to go first.
Hello, my name is Manuel Chakravarti, and I'm a technical architect for smart contracts and related technologies at IHK. And together with Phil and other people, we've developed the Plutus smart contract infrastructure, which just been set live.
Hi, I'm Philip Kant. I've been working on Cardano since a good 4 years ago now, I think. First as a Haskell developer, then building and leading the formal methods group, and now coordinating all the development teams working on Cardano. And yeah, that's me.
And I'm Duncan Coots, and I'm the Cardano technical architect, which means I mostly focus on the node and the things inside the node, ledger rules, etc. And so for my sins, a lot of the design decisions are my fault. You know who to blame.
I'm really excited to be doing this. Back in 1987, I was one of the editors of the original Haskell report, and we had no idea that people serious in industry would be using this a bit more than 40 years later. We're at the point now where people really that need to get computing written down quickly but correctly are making heavier use of functional programming, Haskell and other languages. You will find many banks, such as Standard Chartered, using Haskell and using other functional languages. So it's really exciting to see this moving forward. And Manuel, could you talk about why Plutus ends up being based on Haskell?
So we made the decision to use Haskell as the basis for the smart contract system of Plutus for Cardano, because we thought it's not a good idea to introduce yet another programming language. This is often done in the blockchain space. A new blockchain comes with a new language. Designing a language is quite some work, but it's really even more work to build a community, educational resources, and everything, all the tooling that goes with it. So using existing language, using existing tooling, the existing ecosystem just seemed to make so much more sense. And then Haskell was of special interest due to its purely functional nature. So functional programming has long been used for systems where it's important to be sure that they actually do what we intend them to do, and where it's hard to get them to do something the designers didn't want them to do. And that's especially important for smart contracts because smart contracts contain so much value. They decide over where huge amounts of funds or tokens or NFTs are sent to. So it's really super important for this to work in the way we want it. And that's why functional programming is such a good technology for it. And there's another reason. So Cardano is like Bitcoin based on the UTXO model, on the ledger model which is used for Bitcoin. And that's different to the model which is used by Ethereum, which is based on accounts. And Cardano used the model which has been introduced by Bitcoin because we know that it is a very solid accounting model. It has the advantage that it's easier to parallelize, and it has the advantage that it's easier to reason about. So it's easier to ensure that the ledger and the smart contracts on top of it do what they're supposed to do. And for example, one benefit we get out of this, one direct benefit for the developers, is what we call determinism. What does that mean? It means when I create a transaction, at the moment when I submit the transaction, I do know exactly what this transaction is going to do if it's admitted to the ledger. So this is different to Ethereum because when you submit an Ethereum transaction, maybe somebody else is a bit faster, submits another transaction, changes the state of the blockchain, and your transaction works differently, which may mean it runs out of gas and you lost that money, or other effects that you didn't foresee. In Cardano, that never happens because the system is fully deterministic. So that's one example of how using functional programming with Haskell brings immediate benefit to the ecosystem.
Thanks. So Duncan, Haskell's also used for implementing quite a bit of Cardano itself. Could you say a bit about that?
Sure, yeah. So indeed, I mean, so in addition to smart contract language, which is a programming language, and Haskell has always been brilliant at implementing programming languages, we're using Haskell to implement the node, which is really a kind of systems programming problem, as well as correctness issue. I think it's worth noting to start off with that we're trying to solve a really hard problem and do it correctly. And when you're trying to solve really hard problems, you tend to need to use more advanced techniques and tools. And Haskell provides a really good sweet spot for this. It lets us employ lots of advanced techniques that help us to do what we need to do correctly. But Haskell is still sufficiently practical that we can use it as a systems programming language. It lets us do all the networking, concurrency. It lets us think about performance. It lets us manage resources reasonably, memory, etc., and deal with low-level system issues. So Haskell is actually really a great systems programming language. Now, there are languages which are, sort of more advanced in some ways when it comes to, higher standards of proof. But then they compromise on the practical aspects that we need for systems programming, issues about networking, concurrency, etc. And they're also quite niche. So Haskell provides this really good sweet spot of letting us do really advanced things which help us write correct code with decent performance, etc., and lets us do all these system level things effectively.
And side by side with Haskell and functional programming, we have the whole field of formal methods, where Philip is an expert. So Philip, could you say a little bit about how formal methods have influenced the development of Cardano?
Sure, yeah. I mean, the point is that we're developing financial infrastructure here, and so you have to make sure really that your code is correct, and that also, despite just you knowing that it's correct, or you having some confidence in that it's correct, that you have to provide some evidence so that other people also can verify for themselves and have reason to believe that the code is correct. And so writing formal specifications and then proving properties about the system and showing some evidence that the implementation actually conforms to the specification is very important. And so for the Cardano ledger, for example, we've written a quite readable formal and executable specification, and our users actually go and read those and ask questions about those. Our auditors read them. We provide proofs, some handwritten proofs, some machine checkable proofs about essential properties like money doesn't just get lost in the system and things like that. And so, yeah, that's why we're doing that, because we need to write software that is correct, and we need to write it in a way that everybody else can just see that it's correct and they don't have to trust us for it.
Thank you. So we're just talking about reasoning about things. So reasoning can be both formal and informal. Both kinds are important, right? You need to reason through what's going to happen. So you've just said a bit about how we're using this in the development of Cardano. Are there any additional details you want to give, Philip?
Sure, yeah. So when you want to show that something is correct, then you basically have different levels of formality that you can go to. You can have the kind of the holy grail, where you have a proof where the computer can go through every step, and you have a proof assistant that basically tells you, yes, there is no hole in this proof, everything is correct. And so that's something that we're doing for the most important properties. There's also handwritten proofs that you can do once you formalize your system. And then there are things that are like not exhaustive, but that are somewhat easier to handle and also closer to your actual implementation, like quick check, like property-based testing, where you state a property, and then instead of proving that for a model of your code, you test your actual code against that using generated test data that you generate in a clever way to kind of as exhaustively as possible in a finite time. You try to cover your state space, and then you get basically you get your compiler tells you yes, or yeah, the tests tell you whether that property is satisfied for all the test data, and also in case it is not it's not satisfied, it gives you some kind of minimal counterexample that you can then use to debug your code. And that has two benefits. One is that it is easier to do. You just write the property, you generate the data, and then you see a result. You don't have to meticulously do the proof, which is hard work and can take a lot of time. And the other advantage is that it's tied directly to your implementation. It's not, there is no gap between the proof that you do using some model of your code and your actual production implementation, but it's tested against the implementation that you have. So that's also something that we use quite a lot.
This is you can actually write out proofs in some of these niche languages that Duncan mentioned. So sort of the thing that comes after Haskell is something called Agda that actually lets you write and check proofs. And we wrote out and checked in Agda a proof of the correctness of Plutus core, which turns out to correspond to an old theoretical idea called System F. So the idea is, how do you make a core language that people will still be using in 40 years, because you don't want to do hard forks every other day? And the answer is, we picked something, System F, that was designed back in the 1970s, 40 years ago. In fact, two different people, a mathematician and a computer scientist, discovered the same system. And that's what we're using for Plutus core. And then we wrote out in Agda the proof of type safety that this is supposed to satisfy. And from that, for free, we get an interpreter. And then we can use that interpreter to test our actual compiler against. This is a very nice way in which formal methods in doing proof and practical coding, you don't actually have to prove the practical coding to get benefit from the proof. It can guide it and it can actually let you test as well. So that's me getting excited about stuff. But moving on, so Duncan, how have some of the ideas that Philip is talking about been used in actually developing Cardano?
I think I'd emphasize kind of the social aspects of having proper specifications. You know, the code that we have is like 100,000 lines of code, right? It's a big, complicated system. And one of the important questions in this is, does it do what we expect? Well, what is it that you expect? You need to be able to write what you expect in a concise enough way that people can actually read it and understand it and say, yes, that is actually what we think it ought to do. Because, you know, sometimes there's like, you know, properties that you could test or prove, like the one that Philip mentioned, that what we call the general accounting property, that, you know, money is not created or destroyed in the system, which is great. You know, that kind of property can catch all kinds of mistakes. But there's quite a lot of stuff in a system like this where there aren't properties like that. It's just a question of, is this what you want? And you need to be able to write down and think about and explain to other people and discuss what is it that we want. So having a formal specification that is compact, you know, I said, you know, the code is 100,000 lines. Well, our specification is a mere 50 pages, right? So it's still big. You know, we're not getting away from the fact there's a degree of complexity here, but that is really small compared to the amount of code we have, and that is small enough that we can have that social aspect. I mean, as Philip mentioned, you know, there's people out in the community who read our specifications and argue with us and say, this is, you know, it should be like this, or, you know, you've done something wrong, or, you know, that's something that really helps for that kind of discourse, is having that compact, formal specification, even apart from all the, you know, great things that you might be able to test or prove about them.
Yeah, I think that's absolutely right. And then apart from actually implementing Cardano, we have all these smart contracts. So Manuel, can you say something about whether the smart contracts themselves can benefit from these techniques?
Yes, the development of smart contracts can absolutely benefit from formal methods and related techniques and advanced testing methodologies such as property-based testing. As you just said, In fact, in the development of the smart contract system itself, we have used this technology. We have formalized Plutus Core, the on-chain representation of Plutus smart contracts. But we've also formalized other parts of the system, such as, for example, the use of state machines to write Plutus contracts. And we are continuing to formalize other parts of the system to ensure that they are working as we expect them to work. But formal verification is also useful for smart contract developers. To actually write a formal proof, of course, you need to know that kind of technology, and we are trying to help developers here by providing tools and methodology, and this is something we are actively working on at the moment. But even without full formal verification, there are things we can do. There are things like model checkers or property-based testing, which is a lot easier to use and really applicable for the normal Plutus developer, and you don't have to know too much about the underlying technology. And finally, we are addressing together in a collaboration with the University Utrecht the question of how do we know that a Plutus smart contract written in Haskell, after it's been compiled to Plutus Core, is still doing the right thing. In other words, how do we know the compiler actually does the right thing and it's compiling the program correctly? On blockchains, that's a very important question, because on the chain, you've got a hash of some piece of on-chain code. From that hash, you have to determine whether you trust that contract. But the hash is the hash of the compiled contract. And in order to analyze the contract, you need the source code. How do you know which source code was used to produce that code? So we all know in Ethereum, in Solidity, they use ad hoc approach where basically during compilation, metadata is generated, version of the compiler, context of the compilation, and then you can just try to recompile and hope you get the same code, and then you know you've got the source code. That's a little bit too ad hoc for us. So what we're working on with Utrecht University is a certifier. A certifier is a tool using an automatic theorem prover to show with mathematical certainty that a particular piece of source code in fact led to the generation of the on-chain code, and that compilation was done correctly with respect to the semantics, that is the meaning of the used programming language. And in this way, we get certificates which can be checked by theorem provers, which establish this connection. And that's actually crucial if reasoning about source code should be really meaningful.
Right. And something that I'd like to thank IOHK for is that they are funding a PhD student who's starting with me tomorrow and a postdoc starting soon, who are going to look at this question about how do you go about formally proving properties of smart contracts. I mean, obviously, this is what you want to do, but it's a research question. No one really knows how to do this yet. So I said I'm a research fellow for IOHK. I forgot to mention that I'm also a professor in the School of Informatics at the University of Edinburgh. So we'll be looking at this from the research side. I'm a professor of theoretical computer science, and this is a theoretical idea, but I think it's one that could end up having a lot of practical impact. How do we go about routinely specifying and proving contracts? We're not there yet, but I think we're going to get closer and closer. But not being there yet, right? There's still a lot of stuff that you can do. And Duncan was talking about the social aspects of these things, but also it can help with things like testing. So Duncan, can you say a bit about that?
Yeah, sure. So with the node implementation, obviously, it has to be correct. But again, it's kind of a system level problem. So it's not something where it's very easy for us to make formal proofs about. It's a very messy setting with lots of concurrency and networking and stuff going on. So what we do is we try to separate as far as possible the parts of the system that have a clear, simple mathematical sort of nature to them, like the ledger rules, from the parts of the system that have to deal with the outside world, have to deal with talking to other peers, etc., networks and things. And that makes it much, much easier for us to do testing in a more rigorous manner. So in particular, like with the ledger rules, where we have the formal specification of the rules, we're able to implement them in a way that in Haskell that is very similar to their mathematical style, using pure functions, which makes them deterministic. And then it makes it much easier for us to write tests. And we use this technique called property-based testing, which I've mentioned before, where you generate, rather than writing individual unit tests as is the traditional method, you generate huge numbers of input cases, and you test that a property holds. So for example, I mentioned earlier, like, the property that money is, the total amount of money in the system remains the same, before and after every single transaction, for example. So we can test those kinds of properties of the ledger rules. Now that same idea can be applied in slightly more complicated settings, even when there are some effects. Like, for example, we do the same thing in the consensus and networking code, despite the fact that the consensus and networking is, full of concurrency. Again, we try to separate as far as possible those parts that are, deterministic and pure from the parts that have to be, non-deterministic and concurrent. But actually, even those parts that are concurrent, we're able to do property-based testing, even where there is, non-determinism and concurrency. We run the whole of the node, the whole consensus and network implementation. We run the whole thing in a deterministic concurrency simulator that can run, as well as being able to run it for real. So the exact same code can run for real, and it runs in a deterministic simulator, which makes it possible for us to do the same technique of generating large numbers of inputs, running it, and seeing if certain properties are preserved or violated. And if they are violated, we can shrink those down to the smallest possible counterexamples. And then, imagine doing this in any other setting. You'd found some failure, but how do you even reproduce it if it's deterministic? Well, in our setting, because we ran it in the simulator, we can reproduce it just by running it with the exact same inputs again. The determinism gives you that kind of guarantee, which is extremely useful for finding and then fixing tricky concurrency bugs, which is the kind of thing that absolutely plagues most systems. So yeah, we really get a huge benefit from doing this. We're able to find much, much deeper bugs than we would do by any other technique.
Right. It's really exciting for me to see property-based testing being used so heavily throughout the development of Cardano and Plutus, because it was a colleague of mine, John Hughes, who really got property-based testing in the functional programming community to take off through a paper that he wrote, I think 20 years ago now, on something called Quick Check that built on some ideas in Haskell that I'd helped with. So it's really fun to see these ideas. It started out as theory turning into practice. So
indeed, it's perhaps worth mentioning that John and I have been working together recently on exactly this problem in this area. I mentioned the deterministic concurrency simulator. John and I have been working together. John has been extending the simulator that I wrote to be able to explore multiple different schedules, so that rather than just finding one possible schedule that's deterministic, you can explore what would happen if you reordered these concurrent events. Can we find a different schedule that would cause a bug to be revealed? And that lets us do the same thing even more comprehensively, which is exciting and jolly good fun.
Right, that's exciting work that's both at the edge of research and very much helping in practice. And not only did John come up with these ideas, but now he's been hired by IOHK to help us implement them and also to teach other people how to use them. So I think that's very exciting. I think teaching is really important. So Philip, how do these ideas impact on what the formal methods group is doing?
Yeah, I mean, that separation between like the pure code, the one that doesn't have any side effects and no concurrency, and the rest, this clear separation that Duncan mentioned is what actually makes it feasible to do a formal treatment of the important parts of the system at all. Because, in an ideal world, if you didn't have any time constraints and as many people as you wanted, you would aim for doing like a full formal treatment of the whole system. But that's not our reality. And if you look at systems that do have concurrency or some kind of mutable state, the formal treatment is much, much harder. And so that separation of saying, okay, we formulate the rules of the ledger, which are really what determines where money flows. We keep those, we write those in a functional manner, just as state transition, taking some state of the ledger into another by a well-defined set of transition rules, that is something that we can treat formally and where we can write proofs about and do these kind of things in a finite amount of time. And that was really important to us because that's where you really don't want to have any error. If you have something in the networking stack, then okay, maybe you go out of sync sometimes, or you have some inconveniences, but that's usually not what like destroys people's money. And so we wanted to be really, really careful with the ledger, and that's why we did that separation. For the networking stack and for the concurrent parts, for the consensus part, we primarily rely on QuickCheck, on property-based testing. We also have a small group in the formal methods group that is working out a more formal treatment using a process calculus of these aspects. But that is, as of now, not as close to the actual production code. So they are, for example, they are doing some proofs about some design decisions, some design refinements that we did, going from the paper to something that runs in the real world. So something like, okay, in the research paper, you have the networking functionality as something that just perfectly transmits instantaneously messages from one party to everybody else. And then everybody sends their chains around. And where in practice, you need to do something that you can actually do with real networks, like, okay, asking your peers for headers and then doing chain selection based on the headers and then that. And so they are doing proofs about some observational equivalence of these two things. It gets even harder when you think about performance, and performance is something that is also quite critical for Cardano, because you have these slots and you need to get the blocks through the system quick enough. And so the performance is like it's a functional requirement for the system to actually stay in sync. And so we have a group that is doing performance benchmarking and is basically looking at how does the block propagation work? How does it work when the system is put under stress? And we're also having a small research group together with the University at Louvain working out a domain-specific language for actually formally reasoning about performance and making sure that the design can fulfill your constraints on performance. So there's
we like to remind everyone that it's a hard real-time system, and we need to treat it as such.
Yeah. And yeah, so those are things that are a bit in the future, but I'm very happy that IHK is actually funding these initiatives that are advancing the state of the art, and that will be useful to us in the future.
And then Manuel, so clearly property-based testing is really useful. How does this show up in working with Plutus?
Yeah, talking about QuickCheck, property-based testing, and John Hughes. John Hughes is actually the co-founder of a company called QVIP. And what they do, they provide property-based testing services, if you like. And IHK has contracted them to develop a property-based testing library for Plutus developers. So this is actually something we are shipping together with Plutus. It is already in the Plutus repository, in the GitHub repository. And what this does is a property-based testing framework which allows you to test Plutus contracts looking at them as a state machine. So you have the API endpoints of the Plutus contract, and those can be exercised, and then the property-based testing mechanism runs these endpoints in randomly different order with different data. And it tries to find a way to break the properties of the contract by doing that, which is exactly what somebody would do who is trying to hack the contract. So in this way, the property-based testing framework tries that and allows the developer to be a step ahead. But and this is great technology, and I hope everybody's going to use this. But One nice thing about functional programming and Haskell in particular is that even without all these technologies which maybe to the novice Plutus developer appear like there's all these things you can do and it's not clear where to start and so on. One big advantage of functional programming is it has been designed from the ground up to be easy for human beings, not computers, human beings to reason about the code. Things like what we call locality, that you can look at a function and understand how it's working without looking at the other 5,000, 50,000, 500,000 or 5 million lines of code in your program. That you can look at isolated small pieces of code, just understand them, and that's enough to step by step give you an idea of what the program is doing. So I think these benefits start much earlier, even before you use all this great technology, which makes it even better, just from the very fact that these programs are simply more comprehensible.
Absolutely. So we've been talking about advantages of functional programming, and it has a lot. But I have to admit, there's one thing that's a huge disadvantage to functional programming, which is most people don't know it. So at Edinburgh and at some places we teach Haskell is the very first language students learn. But generally, when people go through their education, they often come out just mainly knowing imperative programming. And people in the world of developers mainly work in imperative languages and know imperative languages. One of the exciting things for me over the last decade or two has been there's been this real rise in developer conferences of developers that are interested in functional programming and want to learn it. So there are more and more ways for people to get up to speed in functional programming, but it's definitely something you have to do. If you've been trained in the imperative style, then learning how to do stuff functionally can be a bit tricky. And for instance, on Twitter recently, we've seen this huge discussion by people they're used to doing things imperatively, and then you face them with the functional style used in Cardano, and they say, oh, it can't do these things. And it's not it can't do these things, but you have to learn these new approaches. Of course, that's a fair bit of work, this education. So one thing that's a halfway point is a model that everybody knows about, theorists and developers, is finite state machines. And there's been some work to leverage that to make it easier to build smart contracts. So, Manuel, could you say a couple of words about that?
Yeah, so we are, of course, conscious of what you mentioned. And we try to make it as easy for Bluetooth developers as possible to get started. And in addition to things like the Bluetooth Pioneers program, in addition to, well, having picked an existing widely used functional programming language which existed for a long time, where there's a lot of teaching material, there's a great community, there's a lot of tools. We've developed an approach of writing smart contracts using state machines. So state machine is, well, what the word means. It's you've got a piece of state, that's your contract state, and then with each transaction affecting the contract, the state is modified from its old state to its new state. And this kind of model, this is in the way you think about it, closer to what an imperative programmer is used to. And that's one reason why we are using this approach. It is, on one hand, actually also quite convenient even for formally reasoning about contract, but it is also closer to what people are used to. So we hope to bridge the gap a little bit in this manner and give people something which is a little closer. And we are also, we already provide a version of the state machine library for people to use. And we have example contracts which show how to do that. But we are busy developing this capability much further and provide more sophisticated libraries and additional tooling on top of that.
So, Duncan, when you talk to the community, what do you see about this tension between imperative programming being the thing that people are familiar with, but functional programming being what we're using and what has all these great advantages if people can be educated to get up to speed?
Yeah, I mean, as you said before, there is a bit of a mind shift between the functional and imperative style, and people kind of have this assumption, which is generally true, that most languages are equivalent. It's just a matter of relearning libraries, which is kind of true within a family of imperative languages or a family of functional, but less so when you cross from one to the other. I mean, in my background, I have quite a bit of experience with doing training for existing professional programmers in how to move over from imperative languages to Haskell functional languages, and so in my experience, someone who's committed to doing it, and is already a professional programmer, understands imperative languages reasonably well, but has an open mind, can do it. If you do it intensively, it doesn't actually take all that long. You can get started up to there's the sort of famous landmark of getting up to monads in Haskell, which is one of the sort of important patterns. You can do that within 2 days, and then you go and spend some more time practicing, etc., etc. So it's not it's not that big, right? Yes, it's a jump, and you have to be aware of it and be conscious about it. But if you go in feet first, it's totally doable, and it doesn't take too long. So I think, we'll have to see how it plays out in the market, really. But I think the advantages of in the smart contract space of being able to have a higher degree of assurance that you're not losing everybody's money. That's a really big thing, and that's worth a lot to people who are building these kinds of distributed applications. So yes, there's a learning curve, but it's clear what the benefits are. So I think it should work out okay.
Great. So we're getting near the end, but what I'm going to do is give everybody a last word. What's the one takeaway that you'd really like people to come away with from this panel session? And Philip, I'm going to go to you first.
Okay. Well, I think if you want to design and implement financial infrastructure, you have to make sure that it's working correctly, and functional programming and using formal specifications and things like quick check and proofs about essential properties are a great way of doing that.
And Duncan.
Yeah, I think, as Philip said, we're solving really hard problems, and it's really important that this stuff is correct. And so, Haskell and functional languages are not a magic bullet, but they let you use clever techniques. They let you use, great ideas, and employ them to write your code in such a way that you can be fairly sure that it's doing what you want. So I think that's the takeaway. You need the best tools to be able to employ the best techniques.
Manuel.
Functional programming and blockchains are actually a match made in heaven. One of the basic concepts of a blockchain is that it's immutable. And that's also the most important property of a functional program. So these technologies, they really go well together, and especially with the UTXO model, which also has a functional flavor, it's actually the natural choice. And yes, for somebody who is used to Ethereum, it's a little bit of a relearning, but I think it's worth it, because at the end of the day, you will be better at writing better contracts more quickly.
Thank you all. Working in functional programming for all these years, it doesn't solve everything, but it is a huge step up from most of what's happening now. And it's so exciting to me to see you guys taking these theories we've developed and putting them into practice and putting them into work every day. And it's not a magic bullet, but it is a huge step up, and it's so exciting to see that. And so I want to both thank you for your time on this panel, but also thank you for all the exciting work you're doing. I'm looking forward to working with you and seeing where this goes next.
Thank you very much.
Thanks.
It was an honor.
Introducing Cardstarter, the first insured launchpad and accelerator for Cardano projects. Our goal at Cardstarter is to connect the Cardano community with early access to the thoroughly vetted projects that launch through our platform. In line with Cardano's ethos, we believe in inclusion, transparency, and building the foundation for decentralized applications that will drive how the economy of the future operates. We dedicate ourselves to providing a high level of due diligence and quality control for the projects that we support entering the DeFi space. This helps protect our community from exposure to much of the risk currently associated with involvement in new DeFi projects. We ensure that projects have a qualified team, are in an advanced stage of development, have great token utility, and economic structure. We also provide incubation services for projects with amazing concepts who may need advisory and development support to be ready to go to market. You can easily stay up to date on Cardstarter and our IDOs by following our Twitter channel or Telegram announcements channel at Cardstarter Announcements, or join in the community conversation in Telegram at Cardstarter. Participating in Cardstarter IDOs is relatively simple. Our community members who hold enough of our utility token, cards, can use them to qualify and register for our IDOs. When a new project is launching through our platform, our community simply needs to visit app.cardstarter.io to stake enough cards tokens to qualify for a tier. Once qualified for a tier, community members can visit pools.cardstarter.io to register for any active IDOs currently in the registration stage. Registration for an IDO will typically be open for 3 to 4 days, allowing people ample time to declare their intent to participate. Following the registration window, there's a 2-day period where the Cardstarter team confirms that the registered participants have provided their KYC info and are eligible to participate. The last stage is a 24-hour IDO event where community members who've registered visit the same pools page to purchase their guaranteed allocation of tokens for the project. Participants will receive the tokens immediately upon purchase, but will only be able to trade, swap, or send these tokens once the project deploys liquidity on a decentralized exchange. Cardstarter welcomes you to join our community and learn about the exciting new projects that are the fundamental building blocks of DeFi on Cardano.